Hello, everyone. My name is Stephen Yin, and I'm from the MSTC program at Paul Laurence Dunbar High School in Lexington, Kentucky. For my 360-hour research project, I worked on non-invasive speech-emotion recognition, using natural language processing to analyze acoustic signals through deep neural networks. For this project, I worked under Dr. Robert Lauder, the Department of Electrical and Computer Engineering at the University of Kentucky. Going into a bit of overview for my project. First, I'll go into an introduction and a bit of background. Then I'll look into my two engineering goals before iterating through my methodology. I'll analyze a few of the results, go into a bit of conclusions before looking into future research. And finally, I'll go into acknowledgements, show my references, and open the floor for any questions you still may have. So going into the introduction. Emotions are an integral part of human beings. And in fact, around 38% of our human emotions can be communicated through speech alone. This is why speech emotion recognition has recently grown, especially within the field of natural language processing. Speech emotion recognition has many applications, particularly within personalized healthcare. With speech emotional recognition being able to possibly pre-diagnose depressive or suicidal patients, it's clear that speech emotion recognition has many possibilities in further integrating our technology into our everyday lives. However, one of the problems that still remains with speech emotion recognition is that it is still quite difficult to extract effective features, and it's unclear which features are the most important in designating the final emotion. And so, going into the background, for my project, I used a model architecture of deep neural networks. Now, deep neural networks are essentially neural networks, but with multiple hidden layers. And this gives it an essentially hierarchical structure. The importance of this is that it now learns certain features step by step, rather than going from an abstract idea as an input into a final emotional output with not many in-betweens. This allows the deep neural network to essentially take in these abstract features, maybe such as male-frequency septual coefficients, and learn from it slowly. First, in its first hidden layer, extracting possibly words, next second layer, maybe finding meaning in sentences before finally outputting our predicted emotion. And by going step by step, it makes it quite well on operating on complex tasks such as natural language processing. Now, one of the worries with deep neural networks is that it is often overfitting on the training data set. However, in order to combat that, deep neural networks often have dropout. And what neuron dropout essentially does is eliminate certain neurons in each layer. And this simplifies the model in order to prevent overfitting while maintaining the model integrity for its final outputs. And here you can see an architecture of the DNN, and on the right-hand side, a DNN with dropout. On the left-hand side, everything is fully connected. All the neurons are activated all the time. But by eliminating just a few of the neurons, you can see how simple the model is, while still maintaining accurate predictions. The next background is digital signal processing. And digital signal processing, or DSP, is a crucial pre-processing step for deep neural networks. And this is because speech features are easily influenced by the speaker themselves. And so we need to have a strong foundation for speech emotional features to have to input into the model in the first place. And in particular, low-level features are the most important. Of these include something called the male frequency septual coefficients, which essentially model the vocal tract of a human and makes it into an analytical form so the model can actually perform on these coefficients and predict. And it turns out that knowing the shape of our vocal tract can actually portray what phoneme we are producing with our mouths. Phonemes are essentially a unit of sound. And by combining these phonemes together, we can find out what words we are saying. And so it's pretty reasonable that a model able to predict what words we're saying can hopefully accurately predict what emotions we are portraying with these words, with enough training. Finally, as part of the background, I'll go into something called data loaders. Now, data loading is often a bottleneck in the process for deep neural networks. And this is because with so much data, it's almost troubling for deep neural networks to implement and call for the data one at a time. And so what data loaders does is they essentially take this as a take the data generation as a batch loading function rather than simply queuing it one at a time. And you can kind of think about this as maybe a line to go through a grocery store. If there's only one line, there can be only one request at a time and one output at a time. But data loaders make this into a vectorized form by having many lines going in at once and many lines going out at once. And so by having all concurrent requests coalesced into one, the data processing scheme shown below can clearly make this a lot more efficient in the data generation for the model itself. So my two engineering goals for this project were: one, to develop an end-to-end deep neural network model given audio data alone that can accurately predict the 6 different emotions from this speech. Next is to determine the most influential acoustic features used to actually predict the emotional class in the model. And this is in order to address the problem in the beginning, that the most effective speech emotion recognition features aren't really well defined. And so this is an overview for my main methodology, and we'll be going into the specific aspects one by one, so don't worry. On the bottom left-hand side, you can see where we're going to start off. The red arrow points to the data set that I used in my project, the CREMA-D dataset. So the crowdsourced emotional multimodal actors dataset, or CREMA-D, is a dataset created over 7,442 different samples from 91 different actors portraying 6 different emotions: happiness, sadness, neutral, disgust, fear, and anger. As you can see from the tables below, Table 2 shows that there's a pretty even distribution of what emotions the samples portray. And it turns out for the CREMA-D dataset, the actors are quite diverse, and it's well split between male and female as well. Perhaps more importantly, though, the semantic contents of the 12 sentences used as speech in this dataset were all rated emotionally neutral. So none of the words included in these sentences could have maybe a major effect on what emotion the model predicted. Next is actually pre-processing the data through the OpenSmile software. So OpenSmile, SMILES meaning speech and music interpretation by large space extraction, essentially takes in raw audio data and produces a feature set of 6,539 different features for every individual audio data. And so once I extracted these features, I used the EMO large configuration through this process in order to obtain this number of features. In particular, the primary features extracted from this program were actually MFCCs, the mel frequency cepstral coefficients. The coefficients range from 0 to 12, with 0 actually representing the lower frequencies, while 12 represented higher frequencies of the MFCCs. Next in the methodology is where most of my research focused on, which is actually the deep learning model itself. And so in the deep neural network model, I first had an 80% training and 20% validation split. And in the deep neural network model, iterating over the many samples, I had 2 hidden layers. First of 1,024 neurons and second of 128 neurons. The hyperparameters used in this model were a dropout set to 5%, a learning rate of 0.001, a batch size of 16, and a ridge regression or L2 penalty of 0.1. And so going back, you can see how these features were implemented into this data loader, and then it was repeatedly resolved for batches of 16, calling over and over again, and then the data were run through the model before finally outputting the predicted emotion. Next, going into what the deep learning model actually used. An important part of this deep learning model was that it used something called the out-of-bound optimizer. And out-of-bound optimizer is important because it trains as fast as a well-validated optimizer, Adam, and as good as stochastic gradient descent. And so essentially it tries to take the best of both worlds by behaving as Adam during initial epochs before transitioning to stochastic gradient descent with a final learning rate. By doing so, in theory, the model is performing much faster than other models, while at the same time maintaining the high accuracy rates by transitioning to SGD later. And finally, came the model accuracy evaluation and the actual feature rank. By using something called Shapley additive explanations, or SHAP. SHAP could essentially measure which features were the most important. And the idea is based off of a game theoretic approach. The basic overall idea is that it takes the subsets of all different features, not including the feature that I'm trying to look at, and then it looks into whether or not adding that feature in has a major impact on the model output prediction. By examining the impact of every single different subset, it can then predict whether or not the model had a major impact on the final emotional output prediction. And so for this project, SHAP values were ranked across all different emotions, and I analyzed which ones were the most important by averaging across the different emotions one by one. And so by doing so, I created a final ranked list, not specific to any emotions, but averaged overall 6 of them in order to see which ones were the most effective in predicting the emotional class. And so going into the results, on the left-hand side, you can see the accuracy results, how my model performed compared to others based on the accuracy evaluation. On the bottom, there's a human baseline accuracy of 40.9%. And then there's also the recently published highest accuracy of 57% by Gallup in 2019. However, my model actually reached a final accuracy of 64.92%. And so this is clearly higher than the rest of them previously. But an interesting thing to note about the left-hand side graph is that there is a disparity between training and validation accuracy. And so when looking at this disparity, I initially thought there must have been some sort of overfitting occurring on the model. And so I examined on the right-hand side the confusion matrix. Confusion matrices essentially show whether or not there is a specific class of emotions that is incorrectly predicted many times. But by the presence of the dark diagonal, it was shown that there wasn't much of an error that was actually happening in the model prediction. And so that issue wasn't much to be worried about. Next, on the left-hand side, there is the ranked feature importance of the top 10 features accumulated over 6 different emotions using the SHAP values. And you can see how on the SHAP value ranked from top to bottom, MFCCs were predominantly the features that had the most impact on the model output. In particular, on the left-hand side, you can see how the first MFCC coefficient was prevalent amongst many of the features that had the most output, that had the most influence on the model. And essentially what that says is that since the first MFCC coefficient is correlated with lower level frequencies, we should be looking at the lower level frequencies when looking into which features are the most important, in comparison to maybe 10, 11, and 12 MFCC coefficients, which are more related to higher level frequencies, which may not contain as much important information as we would like. On the right-hand side, there's a demonstrative graph of what a SHAP value graph looks like for a single emotion, although for the graph on the, for the table on the left-hand side, I averaged across all. And so in conclusion, my model had an overall improvement of 13.89 relative improvement compared to the Gallup 2019 model. By using the DNN with out-of-bound optimizer, this worked to have the highest final accuracy. And once again, the SHAP values indicated that MFCCs were effective features for audio analysis, particularly those with lower level frequencies. And further research for my project can look at random deep belief network architectures, which have been shown to be quite effective with natural language processing. Additionally, I can add protections against environmental background noise in order to hopefully in the future embed this into a real world scenario and possibly implement this into mobile applications so that it can be accessible to a wide range of people. A few acknowledgements I'd like to make. First is to my mentor, Dr. Robert Lover, for helping me throughout this project. Next, to the MSTC Math, Science, and Technology Center program, and of course, Ms. Karen Young, the director of the MSTC program. Next, the KYRP Kentucky Young Researchers Program, and finally, my friends and family, for giving me rides to the lab whenever I needed and pushing me on through the hardest times of this project. Here are a few of my references. And if you have any questions, feel free to email me if you need. Thank you.